Hi everyone, welcome to my talk today about in-situ observation of the structure of crystallizing magnesium sulfate solutions. I'm Chi, working in Axios group at Cambridge, and I did this project with my colleague Johanna Kölbel, and we also received a lot of help from Terry at the University of Southampton. Here's the outline for the talk today. I will first introduce the system we're looking at, the magnesium sulfate hydrates, and then I will introduce you to the main technique we use for this project, the Terahertz time domain spectroscopy. And then I will show you a nice experimental setup we built up specifically for this project. And then I will show you the result and the discussions we got for now. And finally, there will be some conclusions and acknowledgements. So the system of the magnesium sulfate hydrate is very interesting because it has so many different forms of hydrates. But for our project, we start with the heptahydrate because you can crystallize it easily at certain concentrations around room temperature. So on the picture showing on the left side is the crystal we grow in the lab. And you can see around room temperature, you can grow such nice and large crystals. And the magnesium sulfate water system has received a lot of attention recently because it's possibly present on Mars. So for some of you may not be very familiar with the Terahertz time domain spectroscopy, let's start with the Terahertz radiation first. So the Terahertz radiation is located between the far infrared and the microwave regions on the electromagnetic spectrum. Stuff from FTIR that you might be more familiar with, which can probe the functional groups and the certain vibrations. While for the Terahertz time domain spectroscopy, it can probe the inter- and intramolecular motions, make it very sensitive to the structure of the crystals, and can be used for this project about detecting different type of hydrate forms, and also it's very useful for polymorphs as well. So when we do the Terahertz measurements, we first will acquire the time domain waveforms as shown on the left side over here, and via Fourier transform, we can get the power spectrum of both the reference and the samples. And by comparing the spectrum of the reference and the samples, we can get the final Terahertz absorption spectrum. The figure showing on the right corner is the spectrometer we used in our lab, which is Terahertz 4000 by TeraView. Here shows a very typical spectrum of the crystalline material, and it was acquired with the sample of heptahydrate as received. And as we can see, we acquired at various temperatures because the measurement is very sensitive to a temperature background, and also the lower the temperatures go, and the sharper and the more pronounced the peaks are. But unfortunately, for our project this time, we can't acquire the spectrum as low as 80 K when we're monitoring the whole crystallization process. So what we did is we grow some crystals about the same conditions while we do the crystallization process, but just grow the crystals in the film hood. And then we do a various temperature measurement on this sample as well. And as we can see at different temperature, the spectra matched but quite well as we used the sample just as received. It has a peak at about 1.1 terahertz and also another one around 1.6 terahertz. So by this, we can confirm that the crystals we grow at these conditions is heptahydrate instead of other forms. So here shows the system we built up for this project. It's mainly focused on this flow cell, and we will fill the green part with the heptahydrate solution. It is held by a hollow metal sample holder outside of it, and we can circulating water around the sample holder that can change the temperature of the flow cell. And the temperature of the circulating water is actually controlled by the extra water bus and also an ice bus to cooling down the water, and a heater to heat up the water. We have also attached a thermocouple in the water bus to monitor the temperature all the time, and also we have another thermocouple just attached outside of the flow cell to track the temperature of the flow cell all the time. And the Terahertz radiation penetrated through this direction, and we have also got attached the camera to monitor the whole process, so to capture the pictures when the crystal grows. So for this setup, we'll get three main sets of data from Terahertz spectra and the images captured by the camera, and also the temperatures we got from the thermocouple. For now, we have tried 3 different concentrations, and which is the 1.4 to 1, 1.3 to 1, and around 1.2 to 1. And also we did at various temperature. The range is about from 3.6 to 9.5 degrees Celsius. As I said, we get 3 main sets of data, so when we process data, we also do it in 3 different steps. The first one, we only analyze the Terahertz spectra, and the second one, we analyze the absorption at various temperature and frequencies. For this one, we will link the data we got from the thermocouple to the Terahertz spectra. And the third step is to analyze the images, which we will analyze the photos captured by the attached camera, and also we will link the data we got from the camera to the Terahertz spectra. And now I will show a set of data like how we process it to go through the steps. These are the spectra we acquired by Terahertz spectrometer along the time. As you can see at the beginning, because we only have pure liquid solutions in the flow cell, and the dielectric relaxation of the liquid are not coherent, so we can say the spectra is more like a straight line. And when time goes by, the crystal starts to build up. That's when we start to see their peaks showing up around 1.6 terahertz, because the vibrations of the crystals are coherent, and it's more refined to a certain temperature. In other words, refined at a certain frequency. So by the peak emerged at 1.6 terahertz, we can see the onset of the crystals. What we also do is we feed the spectra with the sum of a power law that reflects the amorphous background, and also we fit the peak with a Lorentzian fitting. By this, we determine the onset of the crystallization and the change of the spectral features over time. And now, we start to look at absorptions at 3 different frequencies. At 1.6 terahertz, which is where the peak shows up, and also another 2 at 1 terahertz, where we usually get the highest signal-to-noise ratio, where we're supposed to have the most accurate data, and also another one at 0.5 terahertz, which is at a very low frequency, where it's unlikely to be influenced by the growth of the crystals, but it's more reflected the behavior of the liquid phase. As we can see, when the crystal starts to grow around after 35 minutes, the absorption at 1.6 terahertz increased sharply. That reflects the peaks showing up on the spectra. But at 1 terahertz and 0.5 terahertz, we can see the absorption actually drops a lot after 35 minutes, which means the baseline drops. That reflects the growth of the crystals, so the whole system becomes more ordered than previously. But why the absorption after the growth start to be dropped a bit at 1 terahertz while increased a bit at 0.5 terahertz, we don't know yet, and we're looking into that later. And now is the step 3, where we analyzed the images. The first shows the series of photos captured by the camera. It shows how the crystal grows throughout the time. That's very nicely. And by detecting the edges and also do the binarizing, we can track the whole process of how the crystal grows and how fast it is. The figure showing on the right side, if we define the start of the growth about 10% and the ends of the growth around 90%, the whole process will take about 6.2 minutes for this set of data. But for the Terahertz measurements, because the Terahertz radiation probes from the mid part of the flow cell, so we can only see the crystals when the crystals manages to grow to the mid part of the flow cell. That's why the Terahertz spectrum might only see some features of crystals after the middle point of the growth. And we did a summarizing of all the sets of data we did and all the measurements we did. We did about 40 rounds of measurements, and more than half of them we got crystals, and for sure some of them we didn't really get crystals, as crystallization is such an erratic process. It can also be reflected from our data over here, because we plotted the growth rate at the midpoint at various temperature and also at various concentrations. We cannot really see a clear trend of the influence of concentrations and temperatures. While for some of them we got outliers as being circled over here, that's because we see crystals immediately when we inject the solution, possibly because we already have seasoned the solution when we inject it. That's why the crystal starts to grow immediately. So for now, we can see terahertz spectral was linked very well with the image analysis, and we can see the crystallization process along the time, but that maybe can be achieved by other methods as well. While for the special part of the terahertz measurement is we can see something even before the crystallization, so we can see the clustering and the nucleation of the molecules in the system. As seen here, if we have a pure water, when we feed the spectra, it's more like a straight line as no crystals is showing up over there. But for some of the measurement, we see when we inject the solutions and keep the temperature at a long time and there's no crystal grown after maybe an hour or two. But when we analyze the terahertz spectra, we can still fit a very broad peak around 1.6 terahertz. So that may show the clustering or the nucleation of the molecules in the system, which can only be seen by the terahertz spectra in our dataset. When we have the pure water in the flow cell, or we have the solution, there's no crystal growing in it. When we increase the temperature, the absorption changed generally linearly with the temperature. But for some of the measurements, we increase the temperature in the end, as showing off here. So at the beginning, we keep the temperature around 5 degrees in the flow cell, and then we just switch off the pump. So we let the system to heating up naturally. We can see something very interesting at the beginning. When it's keeping at constant temperature, the absorption fluctuated a bit, around 7.5. But when we increase the temperature in the end, when the crystals are already there, we can see the absorption didn't change for a while until it reached 12 degrees, and it suddenly has a transition point and increased much faster afterwards. So the whole process will be something like here, showing on the right corner. We are thinking if that transition point means when the crystals grows already and the rest of solution are trying to get to a stable state. That's why it shows a transition point at 12 degrees. So here's the conclusion for today's talk. The project applied terahertz spectroscopy to track the whole crystallization process, and it can investigate both the liquid and crystal phase, and it can also provide information before the crystallization happens, so it can show the clustering or nucleation in the terahertz spectra, and which we will focus on in the future. So the first set of measurement we did it on heptahydrate, but the whole system was designed to be operated between 4 to 90 degrees Celsius, and also it can be extended with minor adjustments. And now we are trying to grow other forms of the hydrates as at higher temperature, as low as just below 0 Celsius, to see if we can apply the same setup to other forms of the magnesium sulfate hydrates. And by applying a attached syringe pump, we were also thinking of investigating the steady flow measurement in the future. So here's acknowledgement. Thanks to Terry to help us with the project, and also everyone from Terahertz group. And we are also like to thanks to all of our founding buddies.